So a major disadvantage in most robotic joint applications is the consumption of power from the motor. And so for an artificial limb to be able to hold a load without moving, it requires the motor to supply enough torque to complete the operation. This uses a lot of power, causing the motor to need constant charging and also lowers the motor's long-term effectiveness. And so our team project focused on building a device that would help conserve this motor power for a prosthetic limb while still giving the desired torque. This cog-and-torque element device was created by master student Jacob Amon, whose thesis defined the optimal non-dimensional geometry of the CTE. This device is essentially built with two parts as shown in figure 1 and 2. These figures represent the rotor and stator magnets, and these magnets are oriented every other north and south, and when combined together form a magnetic spring as shown in figure 3. And this magnetic spring gives us the magnetic torque device that we need that will then be connected to a motor. And so the cog-and-torque parallel elastic actuator is created when a motor is put in parallel with this CTE device, which will aid the motor in being able to hold a constant torque without consuming electricity. And this torque is created from these magnets that form a spring-like action that can hold a specific amount of load at each cog. And as that load is overcome, then it switches and rotates over to the next cog and is able to save power while holding that load. And our objectives for building this project and goals are, first, we wanted to make this object small enough that it can fit in a prosthetic ankle or elbow. We also needed it to be able to have a peak torque angle of about 11.25 degrees when rotating. It needed to be able to consume very low power, 1 amp or lower, and it also needed to be able to provide a max torque of 90 Newton meters.
So taking our goal of having our device be small for able to fit into a prosthetic ankle, and taking Jacob Aman's non-dimensional geometry from his thesis, we were able to dimensionalize our CTE device. We then imported this geometry into an ANSYS 3D Maxwell model, in which we were able to run an internal magnetic force calculator. This was able to calculate the internal magnetic forces and torques acting within the CTE device for each magnet. As seen in this figure, the magnetic force was seen all the way around, and in the rotor core, it's very negligible towards the center. Seen in the next figure, the CTE analytical torques were plotted for every angle from -45 to 45 degrees of this thing being rotated. These forces and torques calculated from the ANSYS 3D Maxwell model were then imported into an ANSYS static structural model. This one was to determine the amount of deformation these forces would have on specifically the stator yoke. As seen in this final figure, we can see that the max deformation was roughly at 10 degrees, and at different yoke thicknesses, we had varying levels of deformation. This allowed us to select the smallest size that we wanted while still maintaining the ability to resist this deformation.
So from here, we're designing a prototype that will be utilized for prosthetic ankles. To do this, we first need to find if the CTE torques would be helpful at the angles of the gait cycle. A gait cycle is the movement of a foot, starting with the foot flat on the ground and ending when the foot lands back on the ground. We received this data from Professor Tommaso Lenzi. Using the analytical torque plot from our ANSYS 3D Maxwell model and the angle gait cycle, we were able to calculate the torque applied by the CTE device. Using the known ankle torque and the CTE torque, we calculated the torque a motor would need to provide. We plotted the torques from the motor, CTE devices, and ankle, as seen in Figure 8, to visualize the behavior of each part of the system. To conserve energy, we shut the motor off at 0.75 seconds. This lets the CTE device pull the ankle back to neutral position.
Okay, for our testing setup, we wanted to compare the analytical results from the ANSYS model to the actual prototype. In this figure, we can see the SOLIDWORKS model of our actual testing setup. In this model, we can see our CTE device is attached to another shaft held up by pillow blocks. The collar in the middle of the shaft allows us to attach a wrench and measure the torque. To do this test, we attach the wrench to the shaft with an applied mass to the end of the wrench, shown in the figure. As we increase the weight at the end of the wrench, we measured the displacement in the angle of the shaft using a protractor that is attached to the testing device. This would allow us to plot the actual torque angle curve and find the actual peak torque of the CTE prototype.
Okay, so going into our test results then, our first prototype was assembled and everything went well until we decided we wanted to make sure that it can cog how it should. So we applied torque to it that wasn't measured, and it cogged once, and then the adhesive between the rotor shaft and the rotor core failed, and so the shaft was able to turn when it wasn't supposed to. And so we disassembled our first prototype and put together our spare prototype, but during assembly, then the adhesive between the magnets and the rotor core failed. So we weren't able to measure our peak torque angle or our max torque because of the adhesive failure, but we did reach our objectives for having a small diameter and not consuming any power.
So in conclusion, our CTE device with the magnetic forces was strong enough to hold the high torque as we hoped for, as well as it was able to cog over from one position to another. So the concept is okay, but the problem was that our device failed due to the adhesives not being strong enough. If this project were to continue in the future, then we as a group would recommend to have the following improvements. We say that the rotor shaft and the core would be one solid piece rather than two pieces that are press fit together with some adhesives. And we suggest a stronger adhesive to be used when holding the magnets to the rotor, as well as a thin epoxy to put around the magnets on the rotor, just like is shown with the magnets on the stator. You can see in figure 13 is where the magnets failed and pulled off the rotor, and the gap in between the magnets is shows that. And a huge issue that we had from the ground up was trying to start this running at full speed and with the end goal in mind, trying to get a device that we could attach to a prosthetic ankle right off the bat. The problem with that is there was a lot of components to worry about, and so we ended up taking a step back and going with our pillow block design as shown in figure 9, which is baby steps, allowing us to characterize our parameters before we even add a motor into this, so that we can characterize everything using just the magnetic forces.